Hello everyone, welcome to this lesson. So in this lesson, we're going to go through analytical solutions for 1D and 2D optimization. And we're going to be using the functions that we have introduced in the previous lesson. So let's begin. Now, if you remember, optimization is finding minimums and maximums, and also whether a minimum is an optimum or a maximum is an optimum depends on the function that you're dealing with. If you're dealing with a profit, the optimum would be a maximum. If you're dealing with an error, an optimum would be a minimum. Now, if you also remember, we said that finding an optimum requires two steps. The first step is finding where the derivative is equal to zero, and those are special types of derivatives that we call critical points. And we have said that there are two here, one at negative 3.33 and one at 0. And we also said that these two points have the first derivative in common. So we're gonna have to put in another test to actually define or classify which one is a minimum and which one is a maximum. And we have introduced the second derivative test, and we have also introduced that at a minimum, the second derivative is positive. There's a rate of change positive for the first derivative at a minimum, and also at a maximum there is a negative rate of change of the first derivative. So here the second derivative would be negative. So let's actually begin. So the function that we're dealing with is negative or 4 minus x squared minus 0.2x cubed. Now, the way we find critical points is basically we find where the derivative is equal to 0. So the first step is we get the derivative of this function, and that's going to be, this is going to reduce to 0. It's going to be negative 2x minus 0.6x squared. And then we take this equation and place it equal to 0. We're going to take one x as a common factor, so we're going to have these two factors. So x is going to be equal to 0, and when we put this factor equal to 0, is going to reduce to negative 3.33. So this is how you would find the x values in which the function is equal to 0. And again, we have identified these 2 points. Now the next point is to actually identify the which one is the minimum and which one is the maximum. And basically we're going to get the second derivative at 0 and the second derivative at negative 3.33. So given I have the first derivative here, negative 2x minus 0.6x squared, we're going to take the derivative of that, and that's going to be negative 2 minus 1.2x. Now if I basically take the 0 and put it here, and you're going to find that the second derivative of 0 is negative 2, and since it's a negative, now we have a maximum. And here with the if we evaluate negative 3.33 in this, we find that we get 1.9996. So it is a positive at negative 3.33, which means at negative 3.33 we have a minimum. So it's a very, very simple way to analytically solve for optimums. First, we get the derivative equation, place it equal to 0, get the x values, and then get the second derivative and each one of them. Where it's negative, it's a maximum, where it's positive, it's a minimum. So that's for 1D optimization. So let's actually now move into 2D optimization. Now 2D optimization still has the same two steps. You find the critical points or where the derivative is equal to 0, and you apply a second derivative test. But since you're dealing with a higher dimension function, is going to be slightly more involved, but it's still a very simple technique. So let's begin. So in this function that you see on the right hand side, it's basically f of xy, x cubed plus 3y minus y cubed minus 3x. So this is the equation. So it's basically the function dependent on x and y. And in this case, when you are finding critical points, you are going to be dealing with partial derivatives. We're going to be getting a partial derivative in terms of x. In other words, getting a derivative of this function in as the x being a independent variable and y being a constant. And also here we're going to also take the derivative of this function in terms of y. Now if we take the derivative of this function in terms of x, you're going to find this becomes 3x squared, and this is regarded as a constant, so it drops out. This also drops out, and this reduces to negative 3. So we have 3x squared minus 3, and we place this partial derivative equal to 0, and we're going to find that for this to be equal to 0, we either have a negative 1 or a 1. So here x is plus or minus 1. So we do the same thing for this. This one is regarded as a constant, so it drops out. So we have a 3 remaining from this one, and negative 3y squared from this one. and we place it equal to 0. Again, much like with the x, we have negative 1 and plus 1. So basically we have 4 points in which we have the derivatives equal to 0. We have 1, 1, negative 1 and negative 1, 1 and negative 1, and negative 1 and 1. And this is what is called the gradient. So this is a notation of a derivative when it comes to dealing with a higher dimension, in this case, a 3D dimension here. So these 3 points are our critical points for this function. So if you see, it's basically saying that we have the derivative equal to 0 here, here, down here, and also here. So now we need to define which ones are minimums, which ones are maximums, or which ones are saddles. Now, the second derivative test is going to be defined in this expression here. We're going to call it h. And is defined in terms of fxx multiplied by fyy minus fxy. So what is fxx, fyy, and fxy? Is basically fxx is basically you're taking the derivative that is a function of x, and you're taking another derivative in terms of x. And in terms of fyy, this partial in terms of y, you're going to take another derivative. So the second derivative is going to also be in terms of y. And here, you're basically getting a second derivative, but the first derivative is in terms of x, and the second derivative is going to be in terms of y. So let's actually see how this is going to play out. So here, this is basically fxx, so we're going to take a second derivative of this function in terms of x again. So if you do this, you're going to find this reduces, and this becomes 6x, as you can see down here. And this one, if we take in terms of y, this drops out, is going to be negative 6y, as you can see here. And if we take the fx and we take a derivative of it in terms of y, basically all of this is going to be regarded as a constant, so it becomes a 0. Okay, so now we're going to basically be putting these in here, getting the h for each one of the points. So let's actually take 0.11. So if you take 0.11, the ffx is 6, fyy is 0, and fxy is 0, fyy is negative 6. So basically this is 0, and if we multiply 6 by negative 6, we get negative 36. Now if we evaluate negative 1 and negative 1, basically fxx becomes negative 6. Fxy, you can see, is 0 all the way through for all 4 points. And also fyy, since y here is negative 1, so this is going to be 6. We multiply each by each other, we get a negative 36. Now let's actually look here. 1 and negative 1, fxx is 6, fyy is 6, so I have 36. And negative 1 and 1, negative 6 and negative 6, so again 36. So we have h is negative 36 for 2 points, and negative or positive 36 for 2 points. So let's actually see how do you know whether one is a minimum, maximum, or a saddle. So let's actually see here. If h is equal to 0, you need more information to actually define whether you have a minimum or a maximum or a saddle. So this is this rarely happens, but if this happens, you need more information to define what the point is. But let's actually see here. If h is less than a 0, which means basically we have negative 36 and negative 36, it's a saddle. So you can see here, we have 2 saddles for these 2 points, 1 and 1, and negative 1 and 1, and you can see it's the one here and it's the one here. Now, if h is greater than 0, you have either a minimum or a maximum. So you still have to do a criteria to actually figure out which one is a minimum or which one is a maximum. So at least for the 1 and negative 1 and negative 1 and 1, we know their minimums or maximums. So basically we separated the saddles from the minimums and maximums. So now we have to actually go through this test here. If fxx or xyy is less than 0, it's a maximum. If fxx or fyy is greater than 0, it's a minimum. So less than 0 maximum, greater than 0 is minimum. So let's actually see for this one. So fxx is a 6, so it's greater than 0. This one is greater than 0. So you can see here both fxx and fyy, they're greater than 0, which means I have a minimum as at 1 and -1. And here fxx and fyy, they're both negatives, they're both less than 0. So at this point I have a maximum. So this is how you actually define. So this is the second derivative test in terms of dealing with a 2D function, and you can see it's slightly more involved than the 1D. So that's actually a recap what we've learned in this lesson. We have actually gone through 1D optimization. We found that when you're finding optimums, you go through 2 steps. You find the critical points. In this case, we found the derivative, place it equal to 0, find these 2 points, and also apply the second derivative test to define them as maximum minimum. If the second derivative is negative, it's maximum. If it's positive, it's the minimum. Then we went to 2D optimization, and we found that we still have the 2 steps that we go through, finding critical points and the second derivative. But in this case, it's slightly more involved since here we're dealing with partial derivatives. So we took one in terms of x, and we got x -1 and +1, and also took the derivative or partial in terms of y, y -1 and +1. And we found that we have 4 different points that the derivative is equal to 0, 1, 1, -1 and -1, 1 and -1, and -1 and 1. Now, the second derivative test, we found that is solidified in this h term here. And fxx is basically you're taking the first and second derivative in terms of x. Here, fyy, first and second derivative in terms of y. And fxy, first derivative in terms of x, second derivative in terms of y. And that gave us an fxs of 6x, fyy of -6y, and 0. Then we evaluated all these 3 for all the 4 points, and then we calculated h. We had 2 negatives of -33 and 2 positives, and when h is less than 0, these 2 were saddles. When h is greater than 0, it's either a minimum or a maximum. But here we went through a further criteria. If fxx and fyy are less than 0, which that was in the case for -1 and 1, it's a maximum. If it's greater than 0, it's a minimum. So in the next lesson, we're going to actually start getting into numerical methods and how to actually find optimums using the Newton-Raphson and also the golden section search technique. So that's it for this lesson, and I will see you in the next lecture. Thank you.